Hello, this video will demonstrate the features of the Sunflower 3D solar analysis software. The software supports Rhino 7, Rhino 8, and Grasshopper. Today, I'll be using Rhino 8 to demonstrate these features. The installer's interface showcases the software's main features as it installs. I'll start with a relatively simple file for this demonstration. In this site, the red outline defines the building plot, which is the area we'll be developing. To the side and behind are some existing buildings. However, we haven't modeled the rear buildings with their exact heights, so their specific height isn't clear. There are also existing buildings in front of the project site. Typically, before a developer acquires the land, they'll get the site data from the planning bureau. Then, the design firm gets involved early on to help them with the schematic design. After receiving the data, one key element is the required supporting facilities, which are very important. For example, a community center or a kindergarten. At this stage, we need to use solar analysis to calculate all the relevant planning data. I'll open the solar analysis tool now. In the past, this work might have been done manually by designers. For instance, when I select this building, you can see several very important parameters. Here it shows the total site area enclosed by the red line, and another key metric is the floor area ratio, or FAR. Regarding the FAR, the government sets a limit, for example, requiring the FAR for this site not to exceed 2.6. It provides a limit. When we create a design, we sometimes push this limit slightly. This data on the left is calculated in real time by our software based on the model. If there are many data items, we can use the scroll bar to view them. For instance, we have categories like non-computational floor area. Clicking it lists the relevant buildings. The height and other information for these non-FAR buildings are also clearly displayed here. As another example, the project has a kindergarten as a supporting facility. In the data list, we can find this kindergarten. Clicking it will highlight the corresponding building in the model viewport. When using the software, users focus on both the model and the data. The data list makes it easy to locate models. In other words, clicking an item in the data list automatically navigates the view to the corresponding model. And we can modify parameters directly, for example, by double-clicking the number of floors to edit it. For instance, the originally required facility area might be 1,800 square meters. If the client feels this area is too small or the number of floors is too low, we might need to change the kindergarten's floor count to 6. By changing the parameter, the model updates accordingly. So the model is actually generated dynamically based on the set parameters. The software displays the building's height. Height is crucial in architectural design due to various height restrictions. If we find a parameter was changed by mistake, we can, for example, change it back to the original number of floors. All the metric data on the left, such as the FAR, will update automatically. For instance, after I changed the facility to 6 floors, the total FAR exceeded the limit, turning red, which is obviously not allowed. So it has to be changed back. So the process is like constantly adjusting parameters to see if the calculated data meets the code requirements. If the data complies with the regulations, the scheme is feasible. If it exceeds them, it needs further adjustment. It's an interactive design process. Another issue that users are very concerned about is the unit mix. Developers want to build as many high-profit units, like villas, as possible. They'll ask us to design more villas and minimize the high-rises near the road. We use solar analysis to assist in this process. Now I'll turn on the solar analysis map. Once it's on, we can make adjustments while viewing the solar results. For example, this building gets 4 hours of sunlight, which is plenty. So I can try making it a bit taller or shifting it left or right to test the scheme's feasibility. So this process is really about interpreting data by analyzing the color map. If you feel the quality of the current analysis map isn't high enough, we can make it more detailed. For example, setting the sample distance to 1.0 makes the analysis points denser. This makes the result look more refined. This mode of solar analysis on a 2D base map is a basic feature found in many software. The typical workflow is to place buildings on a base plane and calculate solar access. Our advantage lies in the deep integration between the model, data, and analysis results. For instance, we have a unit mix list here. I might like this 240 square meter villa unit and want to build more of them. To see where these units are located, I just need to click once. The software will then list all buildings using this unit type in the data list on the left. Clicking on Unit A will highlight all buildings containing Unit A in the viewport. Because a high-rise can have a mix of unit types, like Unit A in the middle and Unit B on the sides, it would be very tedious for an architect to find them one by one in the drawings. This makes it very convenient to cross-reference. Additionally, we developed a special feature because we felt that while 2D analysis is good, it has its limitations. Sometimes the project site isn't flat, or the designer wants to check the solar conditions on a specific floor. This is where other software falls short. We developed a 3D rendering mode. We can directly select a region in the viewport to analyze. The first calculation is a bit slower because it needs to build an acceleration structure for pre-calculation. Basically, we aim for a maximum response time of no more than 3 seconds. Right now, it gives a result in about 1 second. This speed is perfectly acceptable for users. We strive for efficiency and hope to provide a great user experience by keeping most calculations under 3 seconds. If the calculation is indeed very large, it might take 5 or 6 seconds. 3 seconds is just our ideal goal. We want the software to be fast because users can get impatient if they have to wait too long. Our current calculations are intensive. An image can have millions of pixels, and we calculate the sun's position for every minute between 8 a.m. and 4 p.m. This is like having 480 lights in the sky, and every pixel is hit by each of them. Even at this megapixel level resolution, our calculation speed is still very fast. If a user finds the current view isn't detailed enough, they can zoom in and calculate again. Recalculating is also nearly instantaneous. We can check the detailed solar conditions for any floor. For instance, here the purple area indicates 5 hours of sunlight, and the blue area has 6 hours, which is in excellent condition. Users can flexibly select any area they want to inspect. I'll turn off the base map's solar analysis. Too many colors can be confusing. I'll move the data panel to the side. Whichever area you select with the mouse, the software will only calculate and display the results for that part. It's like the region render feature in 3D rendering software, rendering only the selected patch. This allows them to observe the analysis results very intuitively. On this panel, real-time analysis is on by default, and you can flexibly select a small region for individual analysis. These next two features, render analysis and inverse envelope, are advanced features available only in the professional and enterprise editions. This render analysis feature can help us render a more refined analysis image. It processes the building outlines, occlusion relationships, and so on very nicely and then exports an image. This feature is designed for users who seek high-quality drawings and are willing to pay to save time. This image overlays the 2D building outlines and handles occlusion, making it clearer than the real-time preview. This last feature is also a very important one, called SunRays. I'll turn it on first, then select a region. This feature shows you which objects are blocking the sun's rays from your point of view. Without this feature, when a designer finds an area with insufficient sunlight, it's hard to determine which building is causing the obstruction. They can only guess what's blocking my light. With this feature on, the obstruction relationship is clear at a glance, which is very convenient. Plus, we can drag this sample point in real time. To check any spot, just drag the point there, it's point and click. This helps them further analyze the solar conditions at a specific point. For instance, if he finds this building is the cause, he might think, since this is blocking it, I'll try lowering it by 2 floors. He can then select that building and lower it by 2 floors in the parameters panel. We also support custom adjustments for things like the analysis map colors. If a user doesn't like the default colors, they can change them. For instance, they can switch to a warm color scheme. All of these are adjustable. And there's the sun path. Sometimes users will question, you say it's blocked, but where is the sun's exact azimuth? Is your calculation accurate? In that case, we turn on the sun path to show them. This way, they can clearly see the sun is here at 8 a.m. and over there at 4 p.m. They can see that after being obstructed, only the sun in the middle segment of the path can shine on this point. The software displays the duration of each continuous period of sunlight. For example, this segment is 1 hour and 52 minutes, and that one is 2 hours and 34 minutes. Finally, there's a summary of the total sunlight duration displayed for this point. Additionally, we support text annotations which can be exported to Auto CAD to generate a drawing style that meets Planning Bureau standards, that is, a window number plus sun hours label. You can click Export to Auto CAD right here to export our analysis results, which they can then take directly to the Planning Bureau for review. After a successful export, a notification will appear. If users find these extra display elements, like the sun path, cumbersome or distracting, we provide switches to turn them all off. Displaying only the core analysis results makes for a very clean interface. Alternatively, you can make the sun path sphere large enough that it's too far away to see, so it won't obstruct the view. To summarize, our solar analysis has 3 core elements: sample points, 2D or 3D, time, date and period, and geographic location. These 3 conditions are all you need. These other display effects, label styles, etc., are all presets we've created for user convenience. Finally, I'll demonstrate the inverse envelope calculation feature from the Professional Edition. This inverse envelope feature allows developers to assess a site's potential in the earliest stages of a project in a very straightforward, foolproof way. For instance, I've just gotten a plot of land, and I know there are buildings in front and behind it. So next to the neighboring buildings that need guaranteed sunlight, we place a row of sample points and tell the software, anything I build on this site in the future cannot block these points or cause their sun hours to fall below standard. Let me show you how. It's very simple to use. You just click this function button. Then you set the solar requirement, for example, ensuring 2 hours, and then set a height limit. Next, select the sample points to be protected and the site's property line, then click OK. The program is now calculating in the background. This step will be a bit slower. Once the calculation is complete, the software generates this envelope. It's like a precisely cut volume telling you that you shouldn't build anything outside of it or you'll block the neighbors. This boundary is pushed to the absolute limit. I'll turn on the solar analysis so you can see. When I move the mouse along the boundary of this envelope, the sample point's sun duration is exactly 2 hours. If I move the sample point just a little bit outside, its sun duration drops below 2 hours. It synthesizes the obstruction requirements of all sample points to arrive at this final form. For example, if we turn on the solar analysis, we can see that the edge of the envelope aligns perfectly with the compliance line. The green area, for instance, indicates that the requirement is just met. This large set of yellow lines in the middle are contour lines. Because many traditional designers are used to working in top view and are less sensitive to 3D space, we generate these contour lines for them so they can intuitively see the height of the envelope at different locations. This calculation is very precise. Sometimes moving just 0.01 meters can change the result from compliant to non-compliant. If I require a 2-hour guarantee, the boundary it gives me is exactly 2 hours. This is equivalent to providing a macro-level guideline for the design, a 3D buildable area where the potential of every location in space is known in advance. So this feature analyzes both the obstruction from surrounding buildings onto the site, and conversely, the future obstruction from the site's buildings onto the surroundings. The fewer obstructions, the greater the design freedom for the site, and thus the higher its value. This tool is more suited for users who are in architectural design but are not solar analysis experts. They can get a general idea of a site's solar potential through simple parameter settings. There's no need to input overly complex or detailed parameters. They can quickly get a generally reliable result. We've collapsed the complex settings so users only see the most important parameter groups, which makes it feel simpler to use. Our metric calculation feature is the same. We strive for simplicity. Users only need to adjust these few core parameters. Other custom settings can be left at their defaults and generally don't need to be touched. For the functions I just demonstrated, you basically click, wait no more than a few seconds, and the result appears immediately. The 3D render analysis in the software is all calculated using the GPU. I'll open the GPU monitoring panel. I will now recheck the calculation, which will be a bit slower, so we can observe the GPU usage. Look, the GPU usage reached 73%. It's almost maxing out. but it finished very quickly in less than a second. The calculation was over before I could even get a good look at the peak usage. This is with a precision of calculating once every minute. From 8 a.m. to 4 p.m., the time interval is 1 calculation per minute. This means the sun's sampling rate is very high. To understand it in terms of rendering software logic, it's like I've placed 480 parallel lights in my scene. Our component layout in Grasshopper is relatively simple. It's mainly divided into a few categories. First is the core analysis module, which contains 5 or 6 different analysis methods. Then there's the parameters module for inputting various settings, and after that, the display module to control the visualization of the results. This section is the data I/O module, mainly responsible for reading data from Rhino or exchanging data between the two. This last one is the help module. If a user needs help, clicking it will redirect them to our official website where they can watch related video tutorials. To help users get started quickly, we provide some simple and clear example files. There are several different examples here. For instance, if I open this example file, it corresponds to the scene I just demonstrated in the Rhino interface. We made a very simple example. After a user opens it, they can basically see the analysis results directly. When they need to perform their own project analysis, the core algorithm part doesn't need to be changed. You just need to replace the input parameters like geographic location and analysis area with your own, right? Yes, just adjust the geographic location and the analysis area. Another example is replacing the input analysis mesh with your own model. This can basically meet most of their needs. If they want to configure more detailed settings, we also provide a wealth of options here in the parameters module. For example, maybe I don't want to see the sun path, or I want to change the color of the analysis map. Or I want to modify the analysis time period. There are many flexible settings here to adjust. We also detect your hardware information, for instance, whether you have a supported GPU, and inform the user. This example file was created, renamed, and saved in a Chinese environment, which is why you see Chinese when you open it. Normally, if I drag a new component in from the toolbar, its language will be displayed automatically based on your current Rhino language settings. The reason this example shows Chinese is because I had already manually renamed it and saved it in the file. Relatively speaking, using the Grasshopper version is very simple. We expose fewer parameter controls to the user, mainly for ease of use, but at the same time, we've left some custom switches for advanced users. Sometimes users still want options they can control themselves, so we kept a few extra. These examples have basically covered the usage of all core components. However, an advanced feature like inverse envelope is not available in the Grasshopper version. Most of the other basic analysis functions are included, and many of the features in the Grasshopper version are provided for free. We've even added some experimental features not found in the Rhino interface version for exploratory users to use for free. But for these non-core functions, I haven't put much effort into deep optimization. Thanks for watching.